All right, this is our last section in chapter 4, and what we're going to talk about is converting between number bases. Now, we've talked about other numeration systems that have other bases, like the Babylonians that had the base 60 system, the Mayans that had that modified base 20 system. But we do use other base systems in our world even now. Do you know of any other bases that are used? We use base 10 in our everyday running arounds of things, but are there any others that you're aware of that are being used? Say again? A week is 7, so we do 7 days in a week, yes, but we don't reset when we get to the end of the week. And we need to reset if we're actually being a base 7 system.
12.
Base 12, what do we use base 12 for? Feet and inches, we do that with feet and inches, yep. Months, yep, because when we reset to the next year, we reset our months again. That's another one we would use it for.
Base 60 in minutes?
Base 60 in minutes. I was going to say there's clocks, right? So our base 60 and our base 12s, or 24s if you're dealing with the like a military style clock, right? There's one more, at least one more.
365.
365 for years. Not one I was thinking of, but you're right. Has anybody heard of binary? Oh, man, all those zeros and ones. Everything that you guys do every single day, and it's in your hand all the time, isn't it? Hardly ever leaves your hand. Your pencils are there now, but even some of you are just like aching to grab your phone, aren't you? Yeah, binary. So all of our technology is done within binary or hexadecimal. Hexadecimal is base 16. So you see hexadecimal used in computer programming as well. So we use number systems. So we're going to talk a little bit about number systems in a general sense, not about specific values. We actually use some of our number systems even with our coins. Like we do have quarters and nickels, right? And things like that with a base 5 system kind of going on. Our base number system with base 10, I like to start by saying that it starts at 0. Inside of my math lab, sometimes it tells you to start with 1. So if it messes up because you start at 0, that's probably why. I'll edit any quizzes and any tests, so don't worry about it from that perspective. Just do what it asks you to do inside of the homework, all right? But we have the digits that go up to what number? What's our biggest digit? Yeah, 9. And then once we hit 9, we exceed the single digits and we have to go to a 2-digit number, right? And our next value, our first 2-digit number, is the value 10. And we keep doing this until we get to 19, and then we go up again. And this process continues. What's the biggest 2-digit number we have? 99, and then we exceed again, and we go to 100. And, of course, the process continues indefinitely. It's the base 10 system you're very familiar with. But the way that our base 10 system works is the way any base system works. It's just that you run out of digits faster, or you have more digits that you get to use. Base 5. Let me first make a comment about base 10. Remind yourself, what was the biggest single digit in base 10? 9. It was not 10. There is no single digit 10 in base 10, right? We call something a 10, but it's not a single digit number. So when we get to any base, it will not have that number in it as a single digit number. There will be no 5 in base 5, there will be no 7 in base 7, and there will be no 12 in base 12. Because there is no 10 in base 10 as a single digit number. Okay? So when I'm working in base 5, I will stop at the number, what do you think? Yeah, 4. No 5s in base 5. We stop at 4. How many digits are there? 5. Just like with us, right? We have 10 digits in base 10, but 10 is not one of them. We have 5 digits in base 5, but 5 is not one of them. We stop just short of the base value's name, I guess you could say. And when we run out of digits, we do the same thing we do in base 10. We go to a 2-digit number. But please don't call that 10. That's the number 10. Crazy stuff. You ran out of digits, right? So what do? Well, you got to use 2-digit numbers. So we would do 1, 1, and then 1, 2, 1, 3, and 1, 4. And after 1, 4, we run out in the ones place. So what do you think would come after 1, 4? 2, 0 first. Yeah. And then 2, 1. And then 2, 2. 2, 3. 2, 4. What would come after 2, 4? 3, 0. What would be our biggest two-digit number in base 5? No nines. Huh? No nines.
94.
Huh?
4, 4.
4, 4. Because 4 is the biggest digit. So 4, 4 would be the biggest two-digit number. The biggest three-digit number would be 4, 4, 4. So what comes after 4, 4? No fives. 1, 0, 0. Man, you can just tell your brains are hurting, right? 1, 0, 0. It is weird. Okay, let's look at base 7. What's the biggest single-digit number in base 7?
6.
6. You guys got it. All right, so we're going to go from 0 to 6. What happens after 6? 1, 0. Until I get to what? 1, 6 is the biggest, and then it would become 2, 0. And it would keep going. What's the biggest two-digit number in base 7? 6, 6. And after 6, 6 would come the number 1, 0, 0. Could you do this for any number, for right now anyway, smaller than 10? Could you do this for base 3? Could you do this for base 8? Yeah, it works the same way. But the next one's a little weirder. Yeah.
Does it continue after 100?
Yeah, it will keep going.
Okay.
Yes, it will keep going just like with ours. How is base 12 different?
That's 2 digits.
It's already more than the digits we already have, right? I need more digits, not fewer digits, right? When I'm dealing with 7 and 5, I just stop. I don't keep going with all the digits I usually have. I stop short. On this one, I actually need more digits than I have, right? So what we do is we go to the alphabet. Okay? So we will have 0 to 9. But I need a number, a single-digit number, that represents 10. And what I do is I go to A. And I need an 11, because that's one shorter than 12. And so I will go to B. At that point, I've run out of digits, because that's the number 11, right? So then I go to 1, 0. And 1, 1. And I go all the way up to 1, 9. And what do you think happens after 1, 9? 1A. And then 1B. And then 2, 0. What would our biggest two-digit number be in base 12? BB. And after BB, we would have the three-digit number 100. Okay, so I mentioned hexadecimal a moment ago. Hexadecimal is as big as the number systems are going to be asking you questions about potentially. Hexadecimal is base 16. So you have a base 16, you need a number for 10, 11, 12, 13, 14, and you need 15. So you need the first 6 letters of the alphabet. Okay, that's what it ends up working out to for base 16. I can't remember if there's actually one in your homework like that or not, but that's the maximum. There won't be any bigger than that. Okay, so the first set of questions we're going to talk about is what happens when we look at the number that comes before and the number that comes after certain numbers in certain bases. So we're going to work within the base system. Our goal is not to turn it into the number that it sort of looks like in our system and then figure out what comes before and what comes after and then turn them back. That's a lot of work. That is not the goal. The goal is to think of it much like I wrote out this list of numbers. As I'm writing this list of numbers, what was before it and what was after it. Typically, one of them is really easy and the other one requires a little bit more work because of the base system that you're in. For example, the first one says 1, 4. Comes before 1, 4? 1, 3. That's the easy one, right? Yeah. So before 1, 4 is 1, 3. What we do to make sure that we're understanding that we're in base 5 is we write the subscript 5 in words beneath it. Okay, like the subscript, yeah? So we write 13 base 5. I'm going to put them in order just so you can see it. 14 base 5 would be next. What would come after, and I said 13 and 14, that was bad. 1, 3, and 1, 4. What comes after 1, 4 base 5?
2 zeros.
It is 2, 0 base 5. So I was asked to find these two quantities, the one before and the one after. A00 base 12. Can you tell me which of the two is the easy one to find this time? The one after. What's the one after?
A01.
It is. It's A01. Okay, so one of them is usually like you almost get it for free, right? What's before 1, 4, 1, 3? What's after A00, A01? You get one of them, it's easy. The other one tends to be more difficult. Because what I want to do is I want to see what comes before this, but I can't just take one away from the 0 because that requires me to change something significantly, doesn't it? So let's think for a moment what we do if the number in our system were something like 900. Just think about numbers in our system. What happens to get the number that's before 900? You have to subtract 1, right? I mean, like that's literally what we do. And in doing so, we actually end up having to borrow or regroup. We talked about that in the last section. So this 9 becomes an 8, and this 0 becomes a 10, from which I borrow 1 to make it a 9, and the 0 here becomes a 10. And then I do 10 minus 1 is 9, and 9, and now it's an 8 at the beginning. So what is literally happening is that instead of having the smallest digit in our system, 0, I end up with the largest digit in our system, a 9, as far as I need it until I can get back over here. Now, if you think about it, we're going to do the same sort of thing in this base. And I'll write it out in much the same way just to mimic what we already did. I'm subtracting. So I need my A to go 1 down. What's 1 down from A? 9. But when I borrow in base 12, think about like inches to feet, how many am I borrowing? 12, right? If you took a foot and you turned it into inches, you'd have 12 inches. So I'm taking one of these away and I'm turning it into something that's worth 12. You're breaking it apart into 12 pieces. So this 0 is now a 12. And I can borrow from a 12, correct? Sure. The 12 can be borrowed from to become an 11. We'll deal with turning it into the right digits in a moment. And this will become the 12 that I was looking for. And I can subtract. What's 12 minus 1? 11. And I'm going to write 11, and I'm just going to underline it to remind ourselves we can't have an 11 as a 2-digit number. I need to change it. But it is subtracted to give 11. In this place, I also have an 11, right? It's 11 minus 0. This is another 11. And then this one's a 9. But I'm supposed to be working in base 12. And in base 12, the number 11 is represented by the letter B. So the 9 is fine, but these are both B's. So the number that becomes before A00 is 9BB base 12. So can you go through the subtraction process? Sure, you can. You can also analyze sort of what's really happening with the digits, right? When I do subtraction in our system, what happens is I end up getting the largest digit. Well, when I take 0, the largest digit is B. And when I move the 0, the largest digit's another B. And I just decrease my A by 1. A was 10, so 1 less is 9. So you can also think of it from that perspective. All right. So we're going to take a look then at a couple of different things. We talked just about moving the number, finding the number before and finding the number after. What we're going to do now is going to feel like what we did back with the Egyptians and the Babylonians and the Mayans and whatever. We're going to take a number in somebody else's system and we're going to put it into our system. We're going to take a number in our system and we're going to put it into one of these other base systems. Okay? This might be one of the videos that you go back and you listen to the verbiage that I'm using, because I feel like the more you hear those phrases over and over again, the easier it becomes to think those phrases as you're working, all right? So this one says to convert the number in some other system, this is the base 2 system, to our system. And then it talks about ways in which to do that. The first thing says by expanding it in powers. That's actually my favorite way of doing it. The second one talks about using a calculator shortcut. You can use a calculator on both of them. It's the shortcut part that's the emphasis on that part of the direction. So let me show you first the powers method, because I think it mimics the things we did with expanded form much better than the shortcut method. So each of these numbers are in a specific base. This one, 1011, is in base 2. So it means I have a 4-digit number. The number is 1011. And each of these place values in our system would be a base 10, but this is base 2. So instead of it being 10 to the 0, it's 2 to the 0. And instead of it being 10 to the 1, it's 2 to the 1. And 10 to the 2, it's 2 to the 2. And 10 to the 3, it's 2 to the 3. Because I'm in base 2. This is not special to 2. I can do this with 6. I can do this with 15. I can do this with 7, whatever. Whatever the number is, I use powers of that number. Okay? And then what we're going to do is we're going to multiply each of these individual pieces together. They get multiplied. So I'm going to actually have 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0. You can put that in your calculator. You can, just exactly like it is if you wish. It might be a bit overkill because these are fairly small numbers to have your calculator really work with them. They're not big. But some of them will be. What if you were working in base 8 and you had 8 cubed and 8 squared? Well, those numbers would get large, right? This one, not so large. And the other thing that's really nice about base 2 is because it's still just 1s and 0s, it's either the base, 2 cubed, or it's nothing, right? So like this one's 0. There's a 0 going on right there. I don't care what 2 squared is. I can do it, but I don't care because it's multiplied by 0. What is 2 cubed? 8. This one right here, 1 times 2 to the first. Well, 2 to the first is just 2. So 1 times 2 is 2. And then what is 2 to the 0? 1. Anything to the 0 power is 1. So this is just the number 1 at the end. And then all I'm doing is adding 8 plus 0 plus 2 plus 1 to give me a grand whopping total of 11. The answer is 11. Okay, so that's not the calculator shortcut part. That's the powers part. I want to show you another powers part before we go back and do it a different way, because I want you to feel that process one more time before I give you another process to think about. Yes?
Just to clarify, it says decimal form, but they're not talking about it with a decimal point.
No.
They mean just base 10. Right?
Decimal is another phrase or another word that means base 10. So decimal means base 10. If you had the word octal, that means base 8. Binary means base 2. Yeah, that's how they're using that word. Thanks for asking. Okay, so let's do the ABCD base 16. Told you a base 16 was going to come up, right? Just like that. Okay, so I'm going to do the same thing I just did. I have a 4-digit number. I have the 16 to the 0 place, 16 to the 1, 16 squared, and 16 cubed. And I am going to definitely want to use my calculator for this, right? I don't want to do 16 to the power 3. I don't know that one. Maybe you do. I don't. All right. I can write ABCD in here. That's fine. But I'm just going to write what they actually are in our value system because we're turning into our values anyway. What's A? A is 10. What's B? 11. What's C? And what's D? 13. All right, just keep a key next to you so you don't have to go counting them all the time. This one was nice because they came in order, but they won't always. And just like before, I'm going to multiply each of these. So I'm going to multiply 10 times 16 cubed. I'm going to write it over to the side just like I did on the other one. It's 10 times 16 cubed plus 11 times 16 squared plus 12 times 16 to the first plus 13 times 16 to the 0. And there's one and only one of these I can do in my head. It's the last one. That's 13. Right? 16 to the zeros ones. This is a 13. So if you wish, you could enter it all in your calculator straight like it is. If you don't want to do that way and you want to find each of the individual pieces, you can do that too. So I don't have each of the individual pieces written out, but we'll get it real quick. So 16 to the third is 4096, and then times 10, this is 40,960. 16 squared times the 11 is 2,816. And then 12 times 16 is 192. And I'm going to add those together. So good, that's what's on my paper. 43,981 is what I have. What you got? Okay, so I like the power system because it mimics exactly what we've already done. It's fabulous. Unfortunately, at some point when my math lab upgraded, it included this shortcut system. It didn't do this about 3 or 4 years ago. It just happened recently. So as much as I don't like this method, I can't exclude it from the direction set in problems. I can't just say, only do this part, don't do that part. It's embedded in there, so I have to show it to you, even though I don't care much for it. It's not terribly complicated. I just don't think that it does a very good job of the understanding of why. I think these are the understanding of why better. I've got bases, they're all powers, it works just like our system. So let me show you the calculator shortcut process. Okay, so this one I'll just shrink for now. All right, to do the calculator shortcut, here's the way that it works. We take the numbers in order, and we simply multiply them by the base. Not the base to the power, but just the base. So I have 1 times 2, and I put it in parentheses. Okay? And then, actually, I lied about that. I start the parentheses. That's what I meant to say. And then what I do is I add the next value that's occurring. It's a 0. And then I multiply this by 2. And I embed another set of parentheses, and I add the next value. It's a 1. And I close that parentheses. And then I multiply this by 2, and I add the next set of parentheses by adding a next value. What was it? Another 1. They're all there. So the numbers themselves are here. Here's 1. Oops. Let me highlight. 1, 0, 1, 1. So if you count, this number at the beginning has been multiplied by 2 here. 1, 2, 3 times. That's the 2 cubed. It's there. All the pieces are there. They're embedded. And this can go into your calculator, if you're really careful with your parentheses, pretty easily. But you have to be really careful with your parentheses. And I don't know many students who are. I forget parentheses too. Another reason why I'm not super fond of the calculator shortcut. Okay? We'll still get the number 11 when we're done. So we're going to practice setting up this ABCD base 16 with that same calculator shortcut. So I start by taking the first number, that's 10, and I multiply it by 16, and I add the second number, which is 11. Okay, so 10 times 16 plus 11, and then I multiply it by base 16, and I add my next digit, so that's a 12. So plus 12, I embed that in parentheses, and I multiply it by my base again, 16, and I add my last digit, it's a 13, and all of that technically would be inside of a parentheses, or you could leave it off at that point if you wished. And I would still get the number 43,981. Calculator shortcut on the other process we're doing is a little bit more friendly. I just find this one to be cumbersome. That's my preference. Yeah. Okay. So far what we've done is we've taken an uncomfortable system whatever the base is, and we've turned it into our comfortable system base 10, right? So what do you think we're going to do next? Go the other direction, right? We're going to start with our comfortable system base 10 and turn it into some other system that we're working with. And there's a really good picture to have in mind. So imagine I come in, and heaven forbid I have 11,028 crayons. And I dump them all on the floor. And we would all go, oh, because it's a big mess. And we want to put them into certain size bags. And the bags have to do with being bags of base 4 size. Okay? So some bags are single leftover crayons. They're 1. Some bags have crayons that are 4 crayons per bag. Some bags have bags that are 4 squared, or 16 crayons per bag. I could have 4 cubed. 4 cubed is 64 crayons per bag. I could have 4 to the 4th. That's 256 crayons per bag. I'm running out of space. Let me shift it. That should say 4 to the 4th, sorry. I could have 4 to the 5th. Not sure if I have that one written down. I do. 1024 crayons per bag. I'm looking to get numbers that are almost as many as what I have. I'll shift that back up in a second. Give me some more space. I could have 4 to the 6th. That's actually 4,096 crayons in a bag. Don't send that many crayons home with my child. 4 to the 7th. And I would get 16,000, I think it's 384. And I'm going to stop. Any idea why I'm stopping? It's bigger than the number I'm working with, right? Okay, so I'm looking at the number 11,028. I need all of the powers of 4 that are bigger. I'm sorry, that are smaller than that, and the ones that are bigger than that I don't need. So I don't need this one, but I will need all of these powers to work with. Okay? Everybody good so far? So I'm working with bags that are certain sizes. The sizes of the bags are based on the base system I'm working in this case, base 4. Now what I'm about to do is going to look familiar because we've done this before. Another reason why I like this particular way of thinking about it. We have, the biggest number is 4,096. And we're going to divide, using a division algorithm, the number 11,028. Do you remember doing this? Yes. Looks just like it, doesn't it? And it will. It'll be exactly what you've done before. You're just using powers of 4 instead of maybe powers of 60 or the modified base 20 powers that we had. Okay? So grab a calculator. You're going to need it, right? It's not a calculator shortcut thing, but you're going to need the calculator. How many times will 4,096 go into 11,028? 2 times. And we put it over there on the right-hand side. What is 2 times 4,096? 8192. And then we subtract. So I don't have all these pieces written out, so I'm going to do it with you. 2836. Thank you. 2836. Okay, we always go down the chain. So we've taken care of 4 to the 6th, which is the 4096. So even if the 1024 didn't go into this one, it does. We're going to divide by it. We did that before too. So we're going to do 1024 over here. It does go into it. How many times does 1024 go into 2,386? Sorry, 836. 2, yes. And if I multiply, I get 2,048. And if I subtract, I have 788. What is the next number I will divide by? Yes, it is 256. Just going down the line, 256. How many times will 256 go into 788?
768.
Huh?
Did I say it wrong?
Oh, you were one step ahead of me. Twice, and then you did the 768. That's okay. Oh, was it 3 times? 3 times, and it's 768. It's okay. Remainder 20. What's the next thing I'm going to divide by? 64, which feels weird because it's not going to go in. That's okay. It's just a 0 over there. No problem. And I would multiply it, and I'd get still the remainder as 20. Then what will I divide by? 16. How many times will 16 go into 20? Once. 1 times 16, 16. Remainder, 4. Now what do I divide by? 4. And how many times does 4 go into 4? Once. And multiply, subtract. 0. Am I done?
Nope.
No. What's the last thing I need to divide by? 1. I still have to do it. I know it's not going to go in, but I have to divide by all of the powers. And here's the cool thing. This didn't happen before. That's your answer. And they're all right there in order. 2, 2, 3, 0, 1, 1, 0. And I need the subscript that says base 4. Say that again? You don't need them in the answer. They wouldn't be wrong, but they're sort of a convention that we use in base 10 that's not showing up to in other bases. Okay, what do you think? Great. At least not too bad, right? Oh, I've got some grumpy faces still going on in the audience. That's okay. Okay, I'd like to show you the calculator shortcut one, though. Okay, and it actually is a fairly nice calculator shortcut. I still like this better because we've already learned this for other systems. I don't have to reteach you anything new. I just showed you how to apply it in a different context. So, you ready to try another one? Okay, so let's see. I don't know that it actually shows up here in the directions. Actually, it doesn't show up in the directions. Here's what I'll do. Let me do one more with this method, and then I will show it to you next time so you can see another shortcut for doing so. It's not necessary for the problems because it doesn't ask the question the same way that they show up, I'm pretty sure, inside of my math lab for the other ones. Let's do one more of these before we quit today. I've got 99,999, and it's a base 9 that I'm trying to put it into. So there are no 9s in base 9. This is a base 10 number, 99,999. But I need to know what the powers of 9 are. So I've got the 1's place and the 9's place. That's fine. And then I have 9 squared. So what's 9 squared? 81. And then I need 9 cubed. What's 9 cubed? 729. How about 9 to the 4th? 65, 61. And that's not all the way up to 99,000, but I think you're probably realizing that you're close enough at this point that anything bigger is going to be too big. Wait, no, do I need one more? Sorry, I'm on the wrong page of my notes. Oh, one more. Sorry, I was on the wrong page. One more, and then I'm too big, yeah. That's the one I wanted. 59,049 is definitely, I can't even get that in but one time, right, into 99,000. So if you want to try 9 to the 6, you're welcome to do so. It will be too big. So we're going to do 59,049. And we're going to divide it into the 99,999. And it will only go one time. So 5949. If I subtract, what do I get? 40950. Okay, what's the next thing I'm going to divide by? 6561. How many times will 6561 go into this? All right, what is 6 times 6561? Say again louder for me.
39366.
If I subtract, what do we get?
1584.
Okay. What do I divide by next? 729. It goes in twice. What is 2 times 729? 1458. And if I subtract, I have 126. Now what do I divide by? 81. 81 goes in one time, so minus my 81. 45. Next I divide by
9.
9. Goes in 5 times, giving me a remainder of 0. Am I done? No. I still need to divide by 1, which goes in, of course, 0 times. And the answer to the question is right here. 162150. And I need to write the subscript base 9 next to it. All right. So